Okay, welcome to lecture 1. Obviously things are a little bit up in the air right now, but this is maybe the best way I can think to approach this problem. I've tried to make sure you guys are actually learning and teaching while we're away. There will be notes provided on Teams, as well as mock papers and a little bit of revision as well. I'm also going to try and do some sort of interactive kind of revisions, which should take the form of kind of quizzes where you would put the answer on online and I'd mark it that way. Whether that would be multiple choice or whatever, I've still to really get to the bottom of, so we'll get to that when we come to it. Obviously this is my house that I'm podcasting from, that I am preparing these videos from. So we might have dogs barking over the top, we might have people coming in, we might have postmen at the door, all those kind of things. I'll do my best to edit those out, but in some cases there might be some minor interruptions, but you're used to that with me anyway. Okay, so lecture 1 is on partial fractions. So we kind of encountered partial fractions in reverse previously. We've looked at things like if we had two fractions being added together. So let's look at some algebraic fractions. Let's say that we had 2 over x plus 3 plus 5 over x minus 5. Just making one up off the top of my head. Well, our usual method to put these together into a single fraction would be to find a way to make these denominators the same. We do that by looking at each partner's denominator. So we look at the denominator here, and what we're going to do is we're going to multiply this by that over that. Because obviously if we had x minus 5 over x minus 5, the same thing divided by the same thing is equal to 1. So I'm not changing the value of anything here by doing this, I'm just kind of stating it in a craftier way. So it's going to be x minus 5 times this fraction here. Plus, and then we're going to do a similar thing to this guy here, but we're going to use this denominator here. Again, because it's the same thing over the same thing, it's equal to 1. And we're multiplying by 5 over x minus 5. So it makes things look a little bit more complicated to begin with, but this helps us out a lot, because I know that the denominator here, once I combine these two fractions together, the denominator here and the denominator of these two combined fractions are going to be the same. X minus 5 times x plus 3 is the same as x plus 3 times x minus 5, thanks to what we call the commutativity of multiplication. We get the same thing no matter what order we do it in. So let's clean that up a little bit. So that's going to be 2 times that is going to be 2x minus 10 plus 5 times that is going to be 5x plus 15 all over, and then I could think really hard about what that times that is, but let's just write it as two brackets, sorry. And then tidy this stuff up. So 2x plus 5x is 7x, minus 10 plus 15 is plus 5. Over that denominator. Okay, so we've taken this stuff here and we've combined it into a single fraction, which in a lot of cases might be very useful. But the concept behind partial fractions is how to do this in reverse, because that can be transformed into that, but it might be that we come to a case where actually we prefer something like this. We prefer something with a very simple denominator. So we might want to take something that's got a complicated denominator that we may not actually see the factors of to begin with, and sort of reverse engineer it. Say, how do we get back to something that looks like this from something that looks like this? So let's draw a line under that, literally. And let's have a look at the example. So let's take a nasty looking thing. Let's do 7x. In fact, let's be interested and redo that thing there. Okay, so I'm starting at the end of the previous example and going backwards. So we're speculating that this thing can become two separate fractions with very simple numerators. Because very often the problem that we've got with this stuff is that the numerator's a bit too complicated, or that there's a bit too much going on between the numerator and the denominator. So we want to simplify the top as much as possible. So we're going to speculate that this thing can become some value a divided by the first factor plus some value b divided by the second factor. And our job now is to find what a and b should be. If we're confident that a and b should be numbers, then this whole equation should be true for whatever we make a and b. It should still be true for all x. So there's a number of little tricks we can play with it after we've done that, but let's have a look at that in a little bit. So what I can do, I'm going to multiply through by this denominator. So it's going to be 7x plus 5. Or if we think about it, it's change the side, change the sign. So this comes up and becomes a multiply times everything that's on the right hand side. Now when I multiply this by that, we're going to have a cancellation. That x minus 5 in the bottom is going to cancel with the x minus 5 in there. And similarly, that is going to cancel with that. So we're going to be left with a. Remember, alright, let's do the whole thing. See if I can fit it in. Yeah, okay. Okay, so everything gets multiplied by a power of that. So this denominator is going to multiply by this thing up here, and this denominator is going to do a similar thing. So then we're left with an equation that says that 7x plus 5 is equal to a x plus 3 plus b x minus 5. So an equation without any numerators, without any denominators, just a straightforward single line of logic. So because this equation should be true, if a and b are just numbers or not functions of x, this should be true for all values of x that we choose. So a and b will be two fixed values, and we'll still make this whole equation valid for any value that we choose. So let's choose some values of x that will help us out. So we can look at this equation and say, well, if I made x equal to 5, that would imply that 7 times 5 plus 5 is equal to a times 5 plus 3 plus b times 5 minus 5. So that's 7 times 5 is 35 plus 5 is 40 is equal to 8a plus, and then 5 minus 5 is 0, so 0b. So arranging that, we get that a is going to be equal to 40, do this in a single line, over 8, which is equal to 5. So I've solved this for A right away. I'm going to do a similar thing for B. We're going to say, well, what if I make x equal to, and you might guess yourself, look at this and guess, well, what am I going to put in that will eliminate, first of all I eliminated B to solve for A. This time let's eliminate A to solve for B. So what value might you put in there to eliminate A? X equals minus 3. Very good. Wish you guys were this good in real life. So that implies that 7 times minus 3 plus 5 is equal to 8 minus 3 plus 3 plus B minus 3 plus 3 plus B minus 3 minus 5, is that right? We'll see in a second. So this implies, and let me just, from my own mentality, clear that up. The minus 7 times minus 3 is minus 21, plus 5 is minus 16. This is going to be 0, and minus 3 minus 5 is minus 8. So that implies that B is equal to minus 16 over minus 8, which is equal to 2. So I've found the values for A and B, and therefore I've found how to decompose this thing into two separate fractions. I found that 7x plus 5 all over x minus 5 x plus 3 is actually equal to, is also equal to 5. So I have to make sure that these numbers I've worked out match up with this here. There's one of the main things that goes wrong here is that you forget which ones are which, or you look at this equation to figure out which ones are which. You have to go back to your initial equation, your initial assumption. This thing here is what we're basing our final answer on. So A is 5, so it's going to be 5 over x minus 5 plus, and B is 2 x plus 3. So that's us. Solved that, and rather happily we've ended up where we started from. These two things match up as if by magic. So we take a fraction, we make essentially an assumption to begin with. We say, well, I'm going to assume that this can be split up into two fractions, one with an A and one with a B, based on the factors on the bottom. So we're factorising the thing in the bottom. If we can't factorise the thing in the bottom, then we can't actually use the partial fractions method. So factorise whatever's in the bottom, make it two fractions, each of which has a denominator equal to one of the factors from the left, the numerator being some value A and B we haven't solved for yet. Rearrange it a little bit, multiply by the denominator, so there's a degree of cancellation that goes on, and we end up with a much nicer equation. And then playing with the values of x so that we can eliminate one of the constants A and B at a time and solve for the other one. Okay, so let's have a look at that. Another example. So let me have a think. Well, let's write about the conditions here. The degree of the numerator must be less than the degree of the denominator. So in other words, the highest power that appears in the numerator must be lower than the highest power that appears in the denominator. Number 2. Denominator must be factorizable. Which is a bit of a looser rule, to be perfectly honest. There's a certain version of these we're going to look at where well, that doesn't have to be true, but the solution becomes a lot worse. A much more kind of gnarly form. Do we have another condition? No, I think that's us. So let's, keeping those in mind, let's have a go at another one. One will do from scratch this time. So 7 minus 8x, I've got a lot of 7s in the brain today, divided by x squared minus 10x plus 16. Okay. So we have a fraction written as a linear factor on the top and a quadratic factor on the bottom. Now this is not meeting our conditions to begin with. It's number 2 is fine. Sorry, number 1's fine, but number 2 we've not met yet. Denominator must be factorizable. So we have to find, ask ourselves first of all, is it factorizable? I'll let you look at that for a second before I tell you. Yes, it is. Maybe think about what that could be factorised into as I write this. So that's going to be equal to 7 minus 8x divided by, so factors that will add to give minus 10 and multiply to give plus 16 would be x. Well, this tells us they're both the same sign, so it's going to be x minus. This should be revision for you guys. Numbers that add up to 10 would be 1 and 9 and 2 and 8 and 3 and 7 and 4 and 6 and 5 and 5. But we need the pair that would multiply to give 16. So that's going to be 2 and 8. So we've done no actual augmentation here, we've just factorised it, we've taken the denominator and stated it in a different way. And we're going to say, okay, I think we can write this as some value a over, a over x minus 2 plus b over x minus 8. And by doing that, we've set up our standard for our partial fractions. So it's 2 fractions, each one with the denominator equal to one of the factors of the denominator to the left. So we're going to kind of jump straight to, we get 7 minus 8x is equal to, so if I multiply a over x minus 2 by all this stuff, the x minus 2 here and the x minus 2 are going to cancel, because remember this becomes a multiply, so all this goes up here, and x minus 2 and x minus 2 cancel, leaving behind this x minus 8. So it's going to be a x minus 8 plus b, and a similar thing happens here. If this comes up to multiply this thing, then the x minus 8 at the top, so it would be here, cancels the x minus 8 at the bottom here, and we're left with the x minus 2. And here we have our formative equation. Let's choose some values to eliminate some stuff. So thinking about what would get rid of, let's get rid of b first. If I put, say, 2 in here, 2 minus 2 gives you 0, so I know that would eliminate b. So x is equal to 2 implies that 7 minus 8 times 2 is equal to a times 2 minus 8 plus b times 2 minus 2. So even though I've skipped some steps, I still am labouring the point here about putting this value in. So 7 minus 8 times 2, which is so it's 70 minus 16, is going to be minus 9. Is equal to 2 minus 8 is minus 6, so minus 6a, and then this is going to become 0, so I can ignore this for now. So that implies that a is equal to minus 9 over minus 6, which is equal to 3 over 2. Minuses cancel and the powers of 3 cancel there. Factors of 3 rather. So that's got our first order values. We can see that this is a fraction. This came out as a fraction. That's fine. All that's going to happen is that we're going to have when we get to the end of it, we're going to have 3 on the top here, and the 2 is going to come down to multiply this factor on the bottom. But we'll get to that in a second. Now let's put x is equal to 8. So that implies that 7 minus 8 times 8 is equal to a times 8 minus 8 plus b times 8 minus 2. So 8 times 8 is 64. 7 minus 64, oh my god, is 57. Yep. This is going to disappear. So it's going to be 6b. Kind of hoping something went wrong there, because that's a big huge number. Oh well. So that implies that b is equal to 57 over 6. Divide them both by 3, it's going to be 19 over 2. And there we have it. We've got our 2 values to insert back in our fraction. So that tells us that 7 minus 8x over x squared minus 10x plus 16 is going to be equal to 3 over 2 over x minus 2 plus 19 over 2 over x minus 8. I mean, I want to neaten that up a bit so we don't have fractions upon fractions. So that's 3 over 2 x minus 2 plus 19 over 2 x minus 8. So that's our answer. That's a fraction that we've devolved this thing into. Okay. So there's a few different cases that we can actually encounter here. If we think about, so these partial fractions can happen for any power on the bottom here. We could do it for cubes as well, in which case we would have an a, a b and a c to try and deal with. But for the time being, I think we're going to concentrate on the quadratics on the bottom. Because the first stage of factorising that cubic is not something we tend to encounter very often either. So let's just look at the things we can actually factorise. So this is fine, because this thing was factorisable into 2 different factors. And if there's 2 different factors, that means there's 2 different denominators in the bottom here, which means there's 2 different numbers we can put in to get rid of one factor, one missing constant at a time. So we can eliminate a, solve for b, eliminate b, solve for a in 2 steps like we did here. But if I were to have the case where this was the same factor twice, so this would be like x minus 2 squared, say. I'd have x minus 2 there, x minus 2 there. I'd also have x minus 2 there and x minus 2 there. And we'd have a case where there's no value of x I could put in here that wouldn't eliminate the other guy. So let's have a look at that. We'll think about how we actually tackle that. So let's do 9x over x squared plus 10x plus 25. Okay, so first of all let's factorise that. Oops, I'm going to sort that out. That's going to be equal to 9x over x plus 5 squared. And again, like I say, if I were to do a over x plus 5 plus b over x plus 5, let's run this through right to the sticky end. This would imply that I'd get 9x is equal to, if I multiply this up here, one of the factors x plus 5 would cancel between there and there. You'd get a times x plus 5 plus b times x plus 5. On k, super, this should be dead easy. I'll just need to stick a number in here, which eliminates a. So I'm going to say x is equal to -5. So that implies that 9 times -5 is equal to a times -5 plus 5 plus b times -5 plus 5. Which obviously tells us that 9 times -5 is 9 minus 45 is equal to a times 0 plus b times 0 is 0. Oh dear, what's went wrong? Uh-oh. It's all went wrong. So this is telling us something profound actually. This is telling us that for this fraction there is no split with the same thing on the bottom that we can actually use. So we have to find a way to solve this that works, first of all. And the method that we found is to say that, well, why don't we just try this thing of different powers? Now it's still going to introduce the same thing, that if we put a number in it's still going to eliminate stuff, but we'll see what happens in a second. So let's, in fact, to have a red pen I can use, let's add a red pen in the mix. Let's do 9x over x plus 5 squared is equal to a over x plus 5, so good, so far so good, plus b over x plus 5 squared. Now, well, it looks like that in this raw form that anything that cancels here is going to cancel with here. You'll see in a second that when I multiply through with this thing, the cancellations are going to happen differently. So that's equal to a times x plus 5 squared over x plus 5 plus b x plus 5 squared over x plus 5 squared. So for this one, that is going to cancel with only one power on the top, and this one is going to cancel with the entire thing in the top. So we end up with this imbalance, which gives us the ability to get rid of one thing without getting rid of the other, because b is not attached to a number now. So let's set x equal to -5. We get 9 times -5 is equal to b, because obviously minus 5 in here is going to cause the cancellation. Oops, smudged the board. It's going to cause this cancellation here. So we're left with this 9 times -5 equals b, which tells us that b is equal to -45. Now there's not much we can do to put stuff in here to cancel, but we've actually solved for b. B's now a value. Since b's a value, that means that we can pick any value for x. So let's rewrite the equation. So 9x is equal to ax plus 5. And then swap out, rather than a plus b, I'm going to write in minus 45. And now if I choose a value for x, I can eliminate everything else but a. So if I say that x is equal to, say, 0, that implies that 9 times 0 is equal to a times 0 plus 5 minus 45, which implies that 0 is equal to 5a minus 45. So a is equal to minus 45 over 5, which is equal to minus 9. Suddenly worried that I've missed something out here. No, nothing missed out. No, all fine. So this means that we can rewrite 9x over x plus 5 squared is actually equal to, again using this thing as our guide, minus 9 over x plus 5 minus 45 over x plus 5 squared. Now it might look like it's just as complicated as before, because the denominator, the biggest denominator if you like, hasn't went away here, but at least the numerators are a lot easier. If the numerators aren't functions of x, then in general it's better for us if we want to do something like integration or differentiation. If these were functions of x, then it would complicate things by quite a bit. It would make the rules we'd have to use to actually do those integrations or derivatives to be much more tricky, much more crafty. But I'm doing a bit of algebra first, which is what all this is, just pure algebra. We've made our calculus job easier if we're wanting to integrate or differentiate these things. So you can see this method is slightly different from the other guy. And it was based on the number of roots that this thing had. So we've got a kind of quadratic theory thing coming in again. Let's try and show you one other type of problem. Let's do no, actually, now that I think about it, that won't be relevant. So let's have a look at, summarise our different methods. So basically, if we look at our quadratic, we can think about it in terms of our discriminant. So if I've got ax squared plus bx plus c, if b squared minus 4ac is greater than 0, this means this thing's factorisable, not using something like complex numbers. If this was less than 0, obviously for the quadratic formula, we'd be square rooting a negative number, and then that would give us solutions that were complex and therefore not the kind of stuff we want to look at in this course. So we use I'm using a again there, should we not use a twice? Let's do alpha plus b over x minus beta, where x minus alpha and x minus beta are the two factors that this thing would factorise into. And if b squared minus 4ac is equal to 0, we can use a over x minus alpha plus b over x minus alpha squared. Okay, so those are our two different situations. One where we've got two different factors, and one where we've got the same factor but used to different powers. And then, as shown previously, there are various ways to solve them because of that. So let's have a look, just before I finish up, let's have a look at a kind of longer one. Well, I'll give us a bit of a help. So we can actually use these things for bigger things, for sort of things like cubics that are on the bottom, but rather than try and write the cubic out, I'm just going to jump ahead and write it in factorised form. So 9x minus 1, I don't know, I've not got much imagination today. It's going to be equal to x plus 2 x minus 1 x plus 3. So I've got this thing with three terms in its denominator, and all I'm going to do is say, well, that is equal to a over the first one plus b over the second one plus c over the bottom one. So sort of same pattern still apply. 9x minus 1 is going to be equal to that, is going to cancel with that, so we're going to get a x minus 1 x plus 3 plus b. Okay, so the x minus 1 out of these three is going to cancel, so it's going to be x plus 2 x plus 3 plus c, and then x plus 3 is going to cancel, so it's going to be x plus 2 x minus 1. So then anytime I make one of these things 0, it'll cancel for everything. So it's actually going to, we don't have to think too hard about it. So for example, let's say x is equal to 1. We're going to get 9 times 1 minus 1 is equal to, well, this is going to, essentially we're picking on the one, all the ones that have this in it. So x minus 1 for x equals 1 is going to give you 0. So that's going to disappear, and that's going to disappear. So we're going to be left with b, 1 plus 2, 1 plus 3. Which implies that 9 times 1 is 9, take away 1 is 8, is equal to 1 plus 2 is 3, 1 plus 3 is 4, 3 times 4 is 12, so 8 is equal to 12. B, which informs us that B is equal to 8 over 12, which is equal to 2 over 3. Let's pick x is equal to, so what else have we got? So we've got minus plus 2 in there, so if I put a minus 2 in there it would cancel, so let's set x equals minus 2. It implies that 9 times minus 2 minus 1 is equal to, so if I put minus 2, there's no minus 2 in there, so that's a plus 2 in there, sorry, so it'll be fine there. But if I put a minus 2 in there, or a minus 2 in there, it would turn to 0 and delete the whole thing. So this factor, this entire term, sorry, and this entire term are going to go. We're going to be left with a. A times minus 2 minus 1 minus 2 plus 3. So 9 times minus 2 is minus 18, minus 1 is minus 19. So minus 2 times minus 1, sorry, minus 2 minus 1 is minus 3, minus 2 plus 3 is 1, so minus 3 times 1 is minus 3, so minus 3a, which tells us that a is equal to minus 19 over minus 3. 19 is a prime number, unfortunately, so 19 over 3. Then finally, let's get rid of this guy. X is equal to negative 3 implies that 9 times negative 3, negative 1 is equal to, so this guy's going to go, this guy's going to go, and we're going to be left with C because it doesn't have an x plus 3 term in it. So C minus 3 plus 2 minus 3 minus 1. So 9 times minus 3 is minus 27, minus 1 is minus 28. Minus 3 plus 2 is minus 1. Minus 3 minus 1 is minus 4. So minus 1 times minus 4 is positive 4, so 4C. So that implies that C is equal to minus 28 over 4, which is equal to minus 7. So this tells us that 9x minus 1 over x plus 2 x minus 1 x plus 3 is equal to, so what was A? A was, so 19 over 3, we've got x plus 2 below A. B was 2/3, so it's going to be plus 2 over 3, b's over x minus 1. And then C was negative 7, so negative 7 over, with no fraction, x plus 3. And that is our answer. So one more before we go, a little sort of a bigger one like this, but a mixed one, just to show you how to do it, to show you how easy it is if you know how to do the previous ones. Let's go 25x plus 9, getting brave, is equal to x plus 8 x minus 2 squared. So in fact we've got 3 factors in the bottom, just one's repeated. So we're going to do, this one's fine, this one we start normally, over x plus 8 plus b over x minus 2 plus c over x minus 2 squared. See what I've done? So basically we've just kind of split it up according to the rules that we established before. We get 1 to do with the separate factor, and we get 2 to do with the repeated factor. And then from then on we just carry on as normal. So 25x plus 9 is equal to, if I multiply this up, I get rid of the x plus 8 there and the x plus 8 there, so it's going to be a times x minus 2 squared. If I multiply this up here, only one of the factors, x minus 2, is going to cancel, so it becomes x plus 8, x minus 2. And for this guy, x minus 2, all the x minus 2 is going to going to cancel, sorry. So it's going to be plus c times x plus 8. So the obvious guy here then, I think, would be to start with x equals 2, because that implies that 25 times 2 plus 9 is equal to, so if I put x at 2 in here, that dies. If I put 2 in here, that dies. And if I put 2 in here, I get 2 plus 8, which is 10c. C times 2 plus 8, which implies that 2 times 25 is 50 plus 9. The 59 is equal to 10c, which implies that c is equal to 59 over 10. Okay, Okay, so let's get rid of the 8s now. So 25 times negative 8 plus 9 is going to be equal to, so negative 8 in here is going to kill that, negative 8 in here is going to kill that, so we're left with this thing, a of x minus 2 squared. Oops, x minus 2 squared minus 8 minus 2 squared. So 25 times minus 8 is going to be minus 200 plus 9 is going to be minus 191. Oh, I've picked bad numbers. It's going to be equal to minus 8 minus 2, it's going to be minus 10 squared, it's going to be 100a. So that implies that a is equal to negative 191 over 100. Ick. So this leaves us in the uncomfortable position where it's kind of hard to pick a value here that will kill it. But we can still, let's set x equals 0. You'll see what happens here. That implies that 25 times 0 is going to be 0, so it's going to be 9, is equal to a times minus 2 squared plus b times a times minus 2, so all I'm doing here is putting the 0 in for here and here and here, plus c times 8. So neaten up a little bit, going to be equal to minus 2 times 0, so it's 4a minus 16b for 8 times minus 2 plus 8c. But I know values for a and no value for c, so that can leave b alone, and that can be the one variable that I actually solve for. So we've got 9 is equal to 4 times minus 191 over 100, I'm hating myself here, minus 16b plus 8 times 59 over 10. So then I'm going to do a big rearrangement here. I'm going to say that b, so I move that here, move that there, and then move the 16 under. That's going to be 4 times minus 191 over 100 minus 9 plus 8 times 59 over 10 all over 16. Now you guys know how much I hate to use a calculator, but I think today's the day. So let's put this in. So 4 times minus 191 over 100 minus 9 plus 8 times 59 for 10 divided by 16 is 191 over 100, would you believe it? Just tell me out in a second, so I'm putting down my answer, I can remember where I'm looking. So that means that 25 x plus 9 over x plus 8 times x minus 2 squared is equal to, where were we for 8? So minus 191 over 100 x plus 8, putting that value in there. b is plus 191 over 100 x minus 2 plus 59 over 10 x minus 2 squared. It's a 3 fractions with 3 simple numerators. So that was a bit laborious compared to other ones, but you can see there's no complicated added bit. The only complication comes from the added arithmetic that has to go on. All we do is we break it up kind of naively. We just say, well, that if it's a individual factor, a distinct factor, it gets its own fraction. If it's a repeated factor or squared factor, we give 1 to each power. 1 for its power and 1 for the power below. Okay, well, I think we'll call it a day for lecture 1. I think maybe I'll add let's do a little question at the bottom here. I'll let you guys have a go at one. Let's have 99 x minus 45. I'm purposefully making this awful, I really apologise. Divided by x plus 3, x minus 9, x plus 4 squared. Okay, so answers on a postcard. I'll maybe put up the solution to that in the days to come. So I would probably appreciate, I'm going to do some edit now, sort of behind the scenes look at how this is going to go on. I'm going to try and edit the video to make it take out any kind of coughs and sneezes I've been doing, but I'm probably going to fail. I'd also like your feedback on how the video's going. Does this format work? Should I use, I've got a big stupid roll of paper that I managed to get from a stationery shop, but it's a bit kind of inflexible, kind of bounces back too easy. So it's a bit of a bother to use, with big markers I could use on it, but to be honest I was quite pleased, I thought, with how this worked on a little test video I did already. So please let me know what you think of this format. Okay, so that was lecture 1 on partial fractions. You'll find notes on the Teams page that will include questions on this stuff. Okay, so I'll see you when I see you, and I'll talk to you soon.